So in the last video, we finished by talking about standing waves that we were going to make in the lab on a string using this apparatus over here. And in this video, we're going to focus on the calculations. What defines the frequency at which that vibrator has to vibrate in order to generate that pattern in the string, okay? And as we said in the end of the last video, only specific frequencies would generate a pattern. Anything that's off from that frequency doesn't. And each of these frequencies are called harmonics, okay? So these are harmonic frequencies, okay? So this original frequency that makes that pattern is my first harmonic. It's my fundamental frequency, or the first harmonic. The second frequency would be my second harmonic. The third frequency would be my third harmonic, and so on, and fourth harmonic, okay? So if I double, triple, or quadruple that original harmonic, I'm going to make these interesting patterns on that string, okay? So what defines exactly what frequency is going to make that pattern? How do we know it's going to be 20 hertz? Okay, well, that relates to the length of the rope. That's going to be a variable. The speed at which a wave travels is going to be a variable that we need to know. And the wavelength, okay, wavelengths on that string. Okay, so for my harmonic, my first harmonic, okay, we get this pattern, which means that that length, the length of that entire string is equal to 1/2 of a wavelength. And you can see a formula written up above here. The length of that string is equal to n divided by 2 times the wavelength, the natural wavelength of that string. And in this case, n is equal to 1 if that's my fundamental frequency, or my first harmonic. N is equal to 2, n is equal to 3, and n is equal to 4 for all the different subsequent harmonics. Okay, so if I plug 1 over 2, 1/2 times the wavelength of that standing wave is equal to the length of the rope for the harmonic frequency. 2 divided by 2 times the wavelength is going to be the length of that rope. So in the second harmonic, the length of the rope is equal to my wavelength. In the third harmonic, I have 1.5 wavelengths for that length. And on my fourth harmonic, I have 2 wavelengths. All right, so that's the general formula for how the relationship between the length of that rope affects the wavelength of the standing wave formed in that rope. And it doesn't matter if I change the length, it's still the same formula. So you can see that my wavelengths are going to become different. And we're going to get to that when we talk about musical instruments. So let's take a look. What defines the frequency? Let's see how we can start doing some calculations. So what we know from the waves unit, okay, is that you have the wave equation that says that the speed of a wave is equal to the wavelength times the frequency, okay? So if I want to find what my frequency of a standing wave is going to be in that first harmonic, I'm going to rearrange this equation. The speed of the wave divided by my wavelength is equal to my frequency. So this is, I'm trying to calculate the frequency of that vibrating speaker. What frequency do I have to set it at? Okay, so I've rearranged my equation and I've created this relationship. Now let's just imagine that the speed of that wave traveling down that rope is going to be something like 200 meters per second. Okay, that's equal to the speed. All right, now what is the wavelength? Well, the wavelength relates to the length of the rope that I set in my experiment, the length. Okay, so wavelength is going to be equal to, if I rearrange that equation, 2 times L over N. Okay, do you guys see how I did that? I just rearranged this equation over here to make wavelength my subject. Okay, so the wavelength is 2 times the length divided by N. And if I'm looking at the first harmonic, N is equal to 1, my wavelength is going to be 2 times the length of the rope. All right, so for my fundamental frequency, if I'm trying to calculate the fundamental frequency, the speed divided by 2L, okay, because that's my wavelength, is going to be equal to my frequency. And in this case, 200 meters per second divided by 2 times, let's imagine that this rope is a 1 meter rope. It's a 1 meter rope, okay? So 200 meters per second times, times 1 meter, if it's a 1 meter rope, is going to give me the fundamental frequency. okay, or the first harmonic. So in this case, I would have 100 hertz is equal to my fundamental frequency. Okay, and then if I wanted to look at what would be the second harmonic, okay, what would be the frequency generated at the second harmonic or the third harmonic or the fourth harmonic? Well, a simple thing you can do is just take your fundamental frequency that you calculated and multiply it by 2 or multiply it by 3 or multiply it by 4. But if I wanted to do the long calculation, I just have to change n in this formula. So for the second harmonic, n is equal to 2, so 2 divided by 2 is equal to lambda. So then for the second harmonic, okay, if I want to calculate the frequency for the second harmonic, it's going to be speed divided by the wavelength is equal to frequency. Speed divided by, okay, it's going to be 2L over 2. Okay, the 2's cancel out because n is equal to 2. Okay, so then my equation becomes speed divided by just the length of the rope is going to be equal to frequency. All right, so then in that case, I'll have 200 meters per second divided by 1 meter, which is the length of the rope, is going to be 200 hertz. Okay, and you can see from that calculation that 200 hertz, which is the second harmonic, really is the fundamental frequency times 2. Okay, and if we would repeat the process for n is equal to 3 and n is equal to 4 by plugging that in here, okay, so 3/2 of a wavelength is equal to the length. If I would plug that into this equation and substitute it here, all right, so 2 over 3 times L would be the wavelength. If I'd plug that in, I would find out that my third harmonic would be 300 hertz and 400 hertz. Okay, so it's a pretty simple calculation. All right, so what do you think, just for you to think about, what do you think would happen to the frequency, the fundamental frequency, if the speed of the wave stays the same, but if I just shortened, if I brought this vibrator closer to the end and I shortened the length of the string, would that frequency go down or would it go up? Just for you to think about. So I want you to answer that right now. Okay, and think about guitar strings. Okay, if you press the guitar string and make it shorter by pressing the tabs down, does the sound go up or does the sound go down? And does that make sense based on these calculations? If I shorten the length of the string, will that make the frequency higher or lower? Okay, and the next thing we're going to talk about in the next video is about the tension of the rope.